Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 24th lecture on linear control. All right, so let's get started with a video. Now the key idea with linear control is I'm going to take my overall robot arm, and I'm going to think about each individual link of that robot. I then am going to develop separate controllers for each one of those links. And that idea kind of reminds me of this video. Now in the video you can see a soft robotic gripper. It's got pneumatic actuation and different soft fingers that it can use to pick up different objects. You can imagine, because of the different actuation and kinematic structure of this system, that you might want to develop a different controller for your gripper than what you have for the other components of your rigid robot arm. So this will be one example of us developing different controllers for different components of our robotic system. All right, so I want to talk about that a bit more in today's lecture. First, I'm going to talk about how you choose controllers for each individual robot joint. And then second, I'll talk about how you can make sure your control gains are going to be stable when you use these linear controllers. Okay, so let's talk about independent joint control. And this is one of the main ways in which we can control robot arms. The idea is I'm going to take my overall robot arm, like what you see right here, and I recognize that this robot has 2 links and 2 joints. But instead of thinking about the entire robot at once, what I'm going to do is I'm going to break it down and try to develop different controllers for each one of these different links and joints. So let's focus in on this first component. Now, I recognize that this has a prismatic joint and a link attached, and I can model that dynamically as a mass damper, where the mass is the combined mass of the link and maybe the motor, and then this damping is perhaps caused by some sort of friction within that motor. I can actuate that motor with a force or torque tau, and I can change its position theta. So I've taken this coupled, complicated robotic system, and I'm looking at just a single joint, which I can now model with linear control techniques. The disadvantage of this approach is that I'm ignoring any interaction between the joints, and those interactions will now become disturbances that are applied to this link. So that would be this disturbance D1 right here. In practice, it might look something like this. So let's focus in on this link of my robot arm. I've got some desired joint position, let's say 45 degrees. With my encoder or other sensors along my robot, I measure its current joint position. I send the difference to my controller. This could be something like a PID controller. It'll output a force or torque, which I send to my motor, and then I use that motor to change my joint position in real time. I don't just do this process once. I do it n different times, once for each individual link of my robot arm. And that's the main idea for independent joint control. Breaking down my robot, looking at each of these individual joints as something that can be modeled with our linear control techniques, and then using these techniques to develop a stable and efficient controller for that joint. So if we understand that general pipeline, how do we go about designing joint controllers that are going to work well for these specific joints? Well, the first thing we need to think about is something called stability. And the reason stability is so critical is that I want to make sure that as I'm controlling my robot, it goes towards these desired positions. It doesn't start to oscillate and maybe break my overall robotic system. So the first thing I'm going to check for is the stability of my closed loop controllers. Now, a linear dynamical system is stable if all the solutions to the characteristic equation have negative real parts. And I refer to those solutions as the poles. So here, this is my standard characteristic equation for our closed loop systems. It's 1 plus CGH is equal to 0. And this includes the transfer functions for my controller, my plant, and my sensor. To give you an example of how this could look, let's look at this equation right here. Imagine that your characteristic equation is s plus 2 times s minus 5 equals 0. Maybe pause the video and think for a second, if you had that, would you have a stable system? Hopefully you realize that no, it would not be stable. One of my solutions is going to be negative 2, which has a negative real part. But the other solution is positive 5, and that has a positive real part. And so overall, one of my poles is in the right half plane. Again, kind of a recap to controls, but if you've forgotten about the left half plane and right half plane, I can show you what they mean right here. So I'm plotting the real axis versus the imaginary axis. And then with these x's, I'm marking the solutions to my characteristic equation. I'm marking the poles. Now, if a system is stable, all of your poles will have negative real parts. In other words, they will all be to the left of this imaginary axis. So you can see them over here. Now, this analysis is occurring in the Laplace domain, but if you want to think about it in the time domain, this just means that my system is going to converge to some steady state over time. Now on the right, I have an example of an unstable system. One of my poles is in the left half plane, and the other pole has a positive real component. So if any of your poles are in the right half plane, your overall system is stable. What this means in the time domain is that you're going to have some exponential that is positive, and it's going to be increasing as a function of time. And so the position of your system will continue to increase and eventually break whatever system you have. So stability is going to be really critical when we're trying to control our robot joints. Okay, so how do I go about figuring out whether a given controller is stable, or maybe how I can pick the gains for that controller in order to make sure that those gains are stable? One really nice rule that we have access to is the Routh-Horowitz criterion. Now, the way you apply this criterion is you take your characteristic equation and you divide it by the leading coefficient, so it looks like this. So let's say your characteristic equation is 5s squared plus 2s equals 0. You would just divide that whole thing by 5, so you'd have s squared plus 2 over 5s equals 0. And then you'd have it in the right form to apply the Routh-Horowitz criterion. Now, there's different rules depending on the order of your system. So if your characteristic polynomial, or this characteristic equation, is a second order system, like you see this s squared right here, then this is the rule you'd want to apply. You'll have it of this form, and you're going to check these two coefficients, a1 and a0. And if both of these coefficients are positive, so a1 and a0 are both greater than 0, your system will be stable. And you can pick any control gains that will satisfy these conditions, and you still will have a stable closed loop system. If this condition is violated, the system is unstable. So it's a really useful condition to check to see whether it's stable or unstable, and you don't actually need to find the poles for this approach. Okay, so that's for a second order system. Now, if you've got a third order characteristic polynomial, like what you see right here, so you've got s cubed somewhere, then you'll be looking at the coefficients a2, a1, and a0. And again, they all have to be positive. And then there's a second rule that a2 times a1 better be greater than a0. If all of these are satisfied, your system's stable. If any of them are not satisfied, you have an unstable system. The same logic applies if you go to a fourth order system with an s to the fourth power in your characteristic polynomial. This can also extend to higher orders, but I'll stop here with the fourth order system. Here are the rules that you'll need to check in order to see whether or not your controller is stable. Okay, so let's practice this concept with an example, and maybe we can use the Routh-Horowitz criterion in order to design a stable controller for our robotic joint. So let's say that I've got one link of my robot. I've isolated this individual link, and I've recognized that I can model it something like a mass spring damper. So here's going to be the mass of that link and joint, and I've modeled it with a damping coefficient K, and then a viscous friction, call that B. Here's the position of my link, and here's the torque that I'm trying to choose in order to control this link. And again, the overall point of control is I want to make my system move wherever it is I want it to go. So I want to pick joint torques that are going to move my robot to some desired position. Okay, so I've modeled my system. And again, this is a single input, single output system. So my input will be my measurement of the joint position theta, and my output's going to be this torque that I'm choosing to apply to my link. All right. So that's the system drawn here, and then over here you can see the transfer function. This is my plant g of s, and it's 1 over ms squared plus bs plus k. In the problem, I'm asking you to find the gains of a PD controller that will result in stability. And you can assume that you have a sensor that accurately measures my joint position theta. So the first step is, let's see if we can just write out the transfer functions for our controller and our sensor. For the controller, I mentioned that I want to look at a PD controller. And so this is one of these PD controllers written in the Laplace domain. I have my proportional gain Kp, and that'll act based on my error in position. And then I have my derivative gain Ks, and that's going to act on my error in velocity. So I've got my PD controller. Then on the right, I've got my sensor, and this is just h of s is equal to 1, and that's because my robot can accurately measure theta, and so the sensor is just passing theta directly back in order for me to make control decisions. Okay, now that I have G, C, and H, I can evaluate my characteristic equation. So right here is my equation for the characteristic equation. 1 plus CGH is equal to 0, and I can just plug in C, G, and H, and I end up with what you see on this second line. I've got 1 plus a fraction, so to simplify this a little bit further, I'm going to multiply both sides by the denominator. So I'll multiply both sides by this ms squared plus bs plus k, and I end up with what you see right here. Okay, so this is my characteristic equation, just simplified down. Now, my last step is I divide by the leading coefficient. So I divide all my terms by m. So I've got s squared plus, we'll call this a1 times s, plus a naught equals 0. And now I've got a second order polynomial. So I can apply the Routh-Horowitz criterion to check and see, is this thing going to be stable? And if so, what range of control gains will make this stable? Maybe you want to pause the video or flip back to the previous slides when we were talking about these second order rules for the Routh-Horowitz criterion, and you can see exactly what we need to do here. Hopefully you recognize that we can actually make this system stable if we satisfy two rules. We acknowledge that the mass of my system is always going to be positive, and so the rules I need to follow are B plus KD, it's got to be positive, and K plus KP has also got to be positive. So I can pick any range of control gains for KP and KD, so long as they satisfy these two rules. Now, if that's for stability. If you want to make sure your system has good performance, in other words, it goes to that desired position very quickly and accurately, you're going to want to tune these gains a little bit more. And that can be a trial and error process, but in general, you probably want to increase your gains for more rapid responses. But just know that when you're actually working with a physical robot, there's an upper limit to what you can do here, because as you increase these gains, you're asking your robot to deliver more torque more rapidly, and at some point you'll reach the limits of what your robot can actually achieve. Okay, so this is an approach I can use in order to find the range of control gains that are going to be stable for my individual joint. Here's a visualization of that process. So on the x-axis, I have time, and on the y-axis, I have my joint position. And this line that you see right here, that's a trajectory that I want my robot to track. So I'm saying this is the position I want to have for this joint as a function of time. In orange, I'm plotting the actual position of my robot if I use the controller we just talked about. And you can see that I've picked control gains that are stable, and so my robot pretty accurately tracks the reference trajectory. So this is us using control to move my robot joint in order to do the task I want to. Now, what happens if I have an unstable system? So here, I've picked some control gains that violate the two terms we just talked about. Now, the video here goes for the first second of the trajectory, and then the plot over here continues that all the way up to 10 seconds. And you can see how the performance gets worse and worse until eventually the system explodes and the position of the link goes off towards infinity. So this, you can see here, an unstable system, and hopefully it's clear why we want to avoid these, because they're going to break our robotic arm and maybe hurt someone who's around that robot. Okay, so in today's lecture, we talked about how you can choose controllers for each individual joint of your robot and how we can use linear control techniques in order to pick those controllers. Now, this was a lot of recap of linear controls, and we highlighted the Routh-Horowitz criterion and how you can use that Routh-Horowitz criterion in order to make sure your controllers are stable. So if you want to practice this a little bit more, I encourage you to check out our practice set. You can see it in the discussion or the pinned comment. The first page has the questions and the following pages have their answers. Once you've gone through that, I want to switch gears and still think about control, but instead of trying to control each individual joint separately, let's see if we can come up with one unified controller for our entire robot arm. So I'll see you in our next lecture.